thank you. As Matt said, it's an honor to be here. I was told when I taught my first class of undergraduates that if ever you're feeling nervous in front of a group and you lose your place, the thing to do is just pretend to take a long sip of your coffee when you look at your notes. It works very well until you, at one point, accidentally drink half of your coffee and have to run to the bathroom. So if you see me chugging coffee, that's probably what's going on. We're going to talk about something called continued logarithms, which are a generalization of the notion of continued fractions. If you know what a continued fraction is, I would invite you to take a nice 1 minute and 30-second long nap while I explain it to those who don't. Please wake up afterwards. It will get more wild and exciting at that point. So, if I want to take a number and write it differently, because I would like to learn more characteristics or properties about it, one way to do that is to take its integer part and its fractional part and write them separately. I can then rewrite this, taking that fractional part and writing that as 1 over that fractional part. I can then write that as 1 over, in this case, 3/2. And now I have another number on the bottom, which is greater than 1. And so I can do the same thing with that number. I can write its integer part plus its fractional part. And actually at this point I'm done, because I'm now left with, in my latest term down here, I have a number who has no fractional part, right? Has a 0 fractional part. And I can continue to do that, right, until I either terminate, which is going to happen for a rational number, or until I go on forever and hopefully discover maybe something that's very interesting. So as you might imagine, some of these continued logarithms, or some of these continued fractions, I should say, can give us very interesting pictures of properties that a number has, which we might not see from its decimal expansion. So here's the square root of 2, which, as you probably are aware, is aperiodic in its decimal expansion, and yet its continued logarithm has this very nice representation. Now, we've done this with lots and lots of interesting numbers. E and pi have very, very cute, nice to look at continued fraction representations. But Bill Gosper wrote a hack memo about 2-3 decades ago, something like that. It's on his website. 4 or 5. Wow. It doesn't have a date on it on the website, or at least that I could see, but John must have talked with him about it at some point in time. But yes, it's very old. I was very amazed to read it and see lots of little, it predated LaTeX, and so I was very amazed to see all of the little the fractions made with underscores and pieced together like this, which some of you just remember reading math that way. So that makes me feel young, I guess. Anyway.
It does feel old.
Thank you. Yes. You're all welcome for that.
I think I triggered that cost rate.
So you could actually think of doing this, right, as following the rules of a dynamical system. Start with a number, subtract copies of 1 as long as you can until you're left with something that doesn't have an integer part, or that has a 0 integer part, right? So count how many times we do that. In this case, we do that 3 times. And then we take whatever's left over, and we divide 1 by whatever's left over, and then we just go ahead and go again. Do it again. We build this, what we call the simple continued fraction, right? Which in this case would look like 3, 1, 2. This is a nice, easy way of writing that. But there's another way to think about building these things, which is with another dynamical system. Maybe you are tired of subtracting 1 over and over and over again. Maybe you have a giant number like Avogadro's number, and maybe you don't even know what the first term of this would be, because you don't know what that last integer would be. Well, you could consider instead just dividing by 2 and doing that over and over again. When you reciprocate, it's going to have to look a little bit different, but you'll end up with some kind of a corresponding continued fraction that looks like this. So I'm going to show you what this looks like for the number 19, and I'm going to show you the construction here. If I take the number 19, I can write number 19 as what I could think of as its leading base 2 term, right? So I can think of it as 2 to the 4th power plus 19 minus 2 to the 4th power. And just like I did over here with a continued fraction with a normal simple continued fraction, I could write this as 1 over 19 minus 2 to the 4th power. I can then multiply both the top and the bottom of this term over here on the right, this fraction, by 2 to the 4th power, and that changes nothing. And then I can divide both the top and the bottom of this term right here by 2 to the 4th power. And what I get is 1 over 19 over 2 to the 4th power minus 1. And this term right here is my new term that I'm going to begin going through this dynamical system with again. So if I rewind the dynamical system, that 1 over x minus 1, that's this guy right here. That x is now 19 over 2 to the 4th power. I've divided a bunch of powers of 2 out of it. And I'm just going to continue to do this. And if I hit the number 1, I'll terminate, which is exactly what happens in the case of 19. If I hit the number 1, I terminate, and I've got this nice continued fractional representation of what I'd call my continued logarithm. One nice thing about this, right, is you can see right away, I'm probably going to end up with smaller terms in terms of the way that I represent this, because instead of these terms simply being integer components, they're being power components, right? This is the number of times that I can multiply 2 by itself and have it go into the number at this particular stage. Okay. All right. For the sake of simplicity, and really just for the sake of not taking up as much space on slides, I might write this as this. Continued fractions are often written this way. The beta terms, we call those numerator terms, and the alpha terms, we call those denominator terms. And so these binary continued logarithms, so far we've only looked at ones where we divided by 2, right? And we're going to keep looking at those for a while, and then we're going to ask what happens if we try to extend this notion to other numbers. But for the time being, when I say binary continued logarithms, that just means we're dividing by 2. Right? So if we look at continued fractions, yes, if we look at the continued fractions, let's go back to slide 16. We can actually write equivalent forms for the continued fractions, right? Just as you saw me multiply the top and the bottom here by 2 to the 4th and nothing changes, I can do this really at any stage throughout the process, as long as what I do is I make sure I multiply a numerator term and the denominator terms by the same number, and that's not going to alter anything. And so with continued fractions, right, this has been done to rewrite pi and e and get these very, very beautiful sort of patterns, these very beautiful and periodic sort of things that really describe these numbers in interesting ways. In the case of these continued logarithms, we were able to use these to show some nice properties. Let's see, if I go down here, there we go, yeah. So we were able to rewrite these as a reduced form continued logarithm, where we take all the numerators and make them 1s, and as a denominator reduced form, where we take all the denominators and make them 1s. And John was able to find a very nice proof using this denominator reduced form to show that the binary continued logarithm for any rational number is going to terminate finitely. So that's very nice, right? You would like it to do that. If you're going to make a rational number, to describe a rational number, you would like your rational number to terminate sometime finitely, right? So you don't want to keep doing this process forever. That would be annoying, and you'd get very tired of it. So that was very nice. And there's the infinite case is a little bit more interesting, right? If we terminate finitely, clearly we have equality. Clearly we've hit the number we were aiming for, because we have equality at every single step all the way up until the end. But in the case where I'm going on and on and on and on and on forever, I want to know that what I'm actually getting, my continued logarithm, I want to know that this fractional form is actually converging to the number that I'm interested in. So we, of course, took many of the classical results for continued fractions, and because these continued logarithms have an equivalent continued fraction form, we were able to take many of these classical results from continued fractions and find their continued logarithm equivalents. And what we were looking for was some kind of a nice proof that we are always going to converge, right, in this infinite case. And actually, after we'd taken many of these things and come up with the continued logarithm equivalence, I stumbled upon this very nice continued fraction result in an unpublished analysis book written by Paul Loya, who was generous enough to share the unpublished manuscript with me. And this result right here, actually all of the convergence for all of our non-terminating continued logarithms, for all of our different bases, not just base 2, but all of the generalizations that we're going to look at here in a few minutes, all of their convergence results fall just immediately out of this. All of the corresponding continued fractions happen to have this very, very nice property. And so this very, very cleanly solves, or it's very, very clean to prove this. Now, another very, very nice thing happens with these base 2 continued logarithms. For the classical continued fractions, there's a distribution that governs what the terms are likely to be, right? If you have some kind of an infinitely going continued fraction, you can predict the likelihood that certain terms will appear by this Gauss-Guzman distribution. And what we actually found was and for that distribution, there is a nice corresponding geometric mean. When I say nice, I mean it's nice when you look at it on screen, but it's not as nice to compute it because you're computing it essentially from the definition. However, for these continued logarithms, we found something that was even nicer, right? Not only do you get a very nice distribution, which is elementary, but you have a corresponding, what we named a Khintchine logarithmic numbers, which are not only easy to compute, they are elementary. Right? So that's easy to compute. That ain't, right? And so this was very, very nice. And so we then naturally asked ourselves, what other kinds of bases could we generalize this idea to? And what happens when we try to do that? And the answer is we quickly run into a little bit of a problem. Right here at this step, where we reciprocated, where we did this, flipped stuff over, got a new number, and went from there, we now have a little bit of a problem, where the dynamical system, if we keep the definition the same, instead of taking us into the interval from 1 to infinity, right, where we now have a number that's bigger than 1, and we're just going to start dividing by 2 again, instead of taking us into that interval, it now takes us to 1/2 to infinity. So in order to the goal is to then fix this, right? Fix this problem with the dynamical system without doing it in such a way that you no longer match the binary case. And depending on how you do that, you can get different kinds of generalizations of the notion of a continued logarithm to base b. And you can have different generalizations that still match in the base 2 case. So with different ones, there are different prices that you have to pay, unfortunately. So here's one way of fixing this. Instead of going to 1 over x minus 1, go to b minus 1 over x minus 1. So in the case of 3, you're just going to have 2 over x minus 1 every time that you flip over and reciprocate. And what that results in, so again, you're dividing by b now, and then instead of having 1 over x minus 1, go b minus 1 over x minus 1, is that you end up, and here's the construction being shown for you. This is basically analogous to what I already did over here. What ends up happening is when you have the continued fraction form written out, it looks like this. You get a bunch of b minus 1s multiplied by all of the b's raised to the powers in the numerator terms. And that maybe feels a little bit arbitrary to you, just slapping a b minus 1 in there to fix the problem with a dynamical system. And it has good properties and it has bad properties. The good news is it does match Gosper's original formulation. And we get a very, very nice distribution, which is shown. So here you are for the base 5 case. A very, very nice distribution. Again, it's still elementary. It looks a little bit fuzzy, but it's still elementary. And you get the nice corresponding Khintchine logarithmic number. The price that you pay is that you're no longer finite for rationals. In fact, if you take the number 2, it just goes on forever with just 0, 0, 0, 0, 0, 0. Basically, you just end up with a giant long string of 1s and fractions that goes on forever. And to me, it felt like maybe this comes from the fact that this is this arbitrary choice of b minus 1 up here. So there's another formulation that we came up with, which is instead.
But 1/3 is 0.3333. We live with infinite expressions for rational. I'm okay with 2 being the infinite thing.
I lose sleep over very irrational things. Anyway, so we decided we wanted to explore more things. So we asked, what about doing it this way? At each step, take the base 3 expansion of the number. Right? So in this case, we're taking the number 89. And what we're going to do is we're going to just lop this first term off of here, 1 times 3 to the 4th, and forget all of the other terms. And then we're going to just start building from there. And again, the construction that you're seeing here is sort of analogous to what you saw over here previously. And what ends up happening is, in the case where the dynamical system takes you into the interval from 1 to infinity, things look like they did before. You just end up with a 1 times 3 to the 4th sitting on top. But in the case where it takes you into that interval from 1/2 to 1, you end up with, if I flip over here, you end up with this sort of a situation where you end up with a 2 up there, as long as we build it under this dynamical system. I will show you the definition of the dynamical system in a moment. It is not pretty. But you end up with that 2 up there, and that saves you, so that you still end up going into the interval from 1 to infinity. And here's what one of these would, continued logarithms would look like. Notice your coefficients, right, are gonna match at each numerator and denominator step based on the fraction. Here's what the dynamical system looks like. It is slightly messy. It's much more pleasant, I think, to look at what the continued fraction looks like. So with this, we again got back our nice finite representation for rationals. But we then lost the nice distribution. We have distributions, and we can see when we got through extensive numerical computation that the distributions, that when you take an aperiodic continued logarithm, the exponents, right, the distribution of the exponents, that's going to conform to these distributions. But finding an actual closed form for these distributions is not so easy. We searched for one, and a student came from Waterloo named Jason Lynch, came for a summer scholar program, and he looked very, very hard for this. And we came up with a recursive way of understanding the distribution, which we thought held a lot of promise, and there was some computational evidence for that. But we then decided to test this by taking the distributions of terms for a whole bunch of aperiodic numbers and seeing if these distributions actually went to the predicted distributions that we had from the work that we've done. And that cast a lot of shade on that. So what experimental computation giveth, experimental computation taketh away. But there is good news, which is that after all of this, he decided, well, what if I go back and instead of thinking about the dynamical system, what if I go back and I just think about the fraction? What if I just think about different ways of writing the fraction? And so from that, I'm going to click over down here. From that, he decided, what if I build this fraction in such a way that my coefficients on my base B expansion, instead of sitting on both the numerator and the denominator, what if they're all just sitting over here on these denominator terms? And in fact, when he did that, we ended up with something where we got to have our cake and eat it too. We get our nice distributions that are nice and elementary, and we get our nice finite termination for rationals. And this is actually a relatively recent breakthrough. I think this happened 3 weeks ago. John was already here, and I was getting ready to leave. And so now they're frantically writing another paper about these. And I really like the overarching narrative of this, because this to me speaks to beyond the sort of innate cultural value of exchanges like this, right? It speaks to the profound academic fruits that these kinds of visiting experiences are likely to bear. So here's the distribution for this type 3, and there's some nice pictures here. I think it looks slightly prettier. Beauty's in the eye of the beholder. So let's talk about experimental computation, since this is an experimental computation conference at any rate. So in terms of actually figuring out what we thought, so this is the binary case we're going back to now. In terms of actually figuring out what the distribution might be, we came up with this notion of, or we didn't come up with this notion of, it already existed, the tail of the continued fraction, right? And so when we looked at the tail of the continued fraction, and we tried to look at the Lebesgue measure of the set of the values, right, in between 1 and 2, such that their nth continued logarithm coefficient was less than zeta for any natural zeta. When we consider that, a whole bunch of very, very happy arithmetic happens that I'm not going to bore you with. But we get a recursive way of seeing the measures of these sets, right? Very easy. It's a very natural notion, by the way, to start in the interval 1 to 2, right? Because now you know that your sum of all of these Lebesgue measures of these sets is going to add up to 1, and also it's essentially all you're doing is you're taking advantage of the fact that at every number, right, at the end of that first step in the dynamical system is going to land somewhere in between 1 and 2, and the first step of your dynamical system is 0% of your total exponents on your terms anyway. So we built this, right, and then fitted to evenly spaced points, and found really good convergence. And originally we considered, we were looking for something of this form. And when that didn't work out, we considered a superposition of two such terms. And Mathematica gave us this, which is somewhat compelling, right? And that looks like about 1/2 for A and 1/2 for B. And we could then, actually check this distribution against what we were actually seeing by computing to a very large number of terms, the continued logarithms for various numbers. And John then found this was already proven in the seemingly different context of random Fibonacci numbers. We found a paper where this has been proven in a totally different context, which is very nice, saves you some work. And so that's basically the experimental discovery. We also looked at quadratic irrationals. So with these quadratic irrationals, these ones that are periodic, because again, not all of them are aperiodic, some of them are periodic. With these ones that are periodic, we found some very interesting palindromes where the terms would actually, they do something like, 1, 2, 3, 4, 3, 2, 1, 1, 2, 3, and so on and so forth. And they have these periods where the periods themselves were palindromes. We thought that was very interesting. We could explore that more. That's something we could do. John and oh goodness, I worked with him for 2 months. John and Jason, thank you, are working on writing a paper about the third way of understanding, or the third general form of the continued logarithms, the third construction for them. And I think that's just about it. I'll go to the cartoon that John always sticks at the end of all of our presentations. And then I'll say thank you. There we go. Thank you.